perspective of theoretical computer science. And so we will explore the graphs using mobile agents. So mobile agent in our language is like some entity that has some computational power. It has some, like, let's say, a processor, and it can perform some moves inside this environment in which it's deployed. So such agents can be like a theoretical model of some software agents, like web crawlers that can travel across, let's say, a hyperlinks in the network of websites, or like a physical robot that's moving around some environment. And this environment is typically either discrete, like let's say a network of computers, or continuous, like some subset of a plane. And in this and people in the theoretical computer science study both models. And in this presentation, we will focus on the discrete one. So the environment will be a graph. Yes, so a graph is a set of nodes and edges that connect these nodes. And this is, let's say, more or less how it looks like. We have an agent that is this little device that can visit the vertices of the graph, and at any, let's say, step of this algorithm, it is located at some node. It can perform some computation based on its, let's say, local information. I don't know, for example, the degree of the node or something else. And then it decides about its next move. So it can move to a neighbor of this, of its current location. And then it takes this, makes its step, and this traversal of one edge is typically assumed to take one step. So this is like one round. At the beginning, it does some computation, makes some decision where to go, then it chooses a destination, and then it makes a step. And some people consider also asynchronous versions where it's this length of the step is different. But we will study like synchronous ones where just one time step is sufficient for agent to just traverse one edge, and each edge has equal length, so it's always one step. And people study a lot of various like models of these agents, and they typically vary with the features of the agent. So the agents very often, and it's actually one of the most important features, have some memory, have some local information that they can store or remember. For example, when they visit a node, they can remember its degree, its number of the number of neighbors this node has. Yes? So the number of outgoing edges from this node. So it can remember this information in its local memory. And when the agent decides to move to some neighbor, it can remember what was the degree of the previous node. And this information is actually very useful. This is sufficient to speed up certain random exploration processes. So even this simple information about the degrees, I mean, comparing the degrees, is enough to speed up some processes. So if we have multiple agents, things are getting way more interesting, because you need to analyze some sort of interactions between them. And one important feature is, can they communicate somehow? So do they have any means of sending messages to each other or communicating with each other? Typically, we study local communication, so meaning that they can exchange information when they are at the same location, at the same node. The third
Sorry, can I interrupt you for a while and ask a question right now, or you
Sure,
prefer...
sure, yes,
Yeah?
definitely.
Okay. So if you have multiple agents, you use still the synchronous updating, but now synchronous updating means that you really update all these agents at the same time?
Yes, yes. So again, people study both. So sometimes you can study that one agent moves faster than the other, but in this talk and in most of my papers, we just assume that they all take steps simultaneously. Yeah? So they all decide at the same time and they take these steps at the same time. Does it answer your question or?
No, for me it's fine. Yeah, I think that everybody understands it.
Okay, so yeah, so and the third feature is the ability to interact with the environment, like for example, leaving some marks, informations, messages for other agents that, for example, this node has been explored or something like this. So the third thing is to whether they can interact or do something inside this environment. And the last two features are perhaps not so commonly analyzed in the context of graph exploration. So the visibility, meaning that they have some radius of vision and they can see, for example, the locations of other agents if they are nearby. And finally, you can think about having a map of the graph, like so knowing the topology. So this is maybe not the most useful, because what's the point of exploring if you already have the map? So we in this talk we will focus on the first three, so the memory, the radio, and the interactions with the environment.
Can I ask the question about this local memory? This is memory of the agent?
Yes.
Okay.
Yeah, so each agent has some memory. Yeah, so maybe local is not the most fortunate word here.
Yes,
it's memory. Yes,
okay.
it's just memory. Yes.
Okay.
Yes, exactly. So and the problem that we study is the exploration. So we have a graph that is undirected, which means that every edge can be traversed in both directions. Yes, so they don't have the edges are undirected, and labeled, meaning that the agent can distinguish the nodes. So you can think that the nodes have some identifiers, and this is sometimes necessary in some of the presented algorithms. And the task, like the objective, is to visit every node of the graph by some agent. So we don't require that every agent, the same agent visits everything. They can obviously divide the work between themselves, but we just require that every node is visited by someone. And you can think of this problem as some from some more practical applications. You might deploy some multiple agents to gather some statistics about the network or perform some maintenance.
So of course you also, sorry to interrupt you again. So of course you assume that it's not only undirected and labeled, but also connected.
Yes, definitely. Yes, connected. It's true. Yeah, if it's not connected, then then you cannot get there. But maybe you have multiple teams in each component. But then you have just several instances of the problem. Yes, you assume it's connected. And what we want actually, since we are doing distributed computing, is we want to benefit somehow from having multiple agents. We want to do it faster. And then so if we have only one agent, then it's somehow simple. In a sense, like it's algorithmically easy to propose some algorithm, and if we have multiple agents, it's slightly more challenging, but we might hope for some benefit, like hope for some faster exploration. And this is how it looks like. So we have a team. Let's say in this example, a team has two agents, and they they are moving in synchrony. So they both decide at the same time and take the steps. And it may happen that they end up at the same node. And two, I'm not sure if I'm going to have enough time to cover both of them, but the two models that we would like to study differ in where the information is stored. So in the first part of the talk, we'll talk about the model where the agents have memory, and in the second one, we'll talk about the model where the nodes have some memory, in the sense that the agents can interact with the environment. And the second model is somehow more like a process, so that the environment is directing the agents, and the agents have no somehow no freedom. They just follow the directions of the environment.
Yes, a question, if possible.
Yes.
The agents are placed randomly in the network, or they have the options to select the initial placement?
So yeah, so typically we assume that that it's the worst case initialization, that we want to do as fast as possible the exploration time, and the initialization is chosen so that it maximizes the time. Yeah, so
adversary.
Let's say, yeah, it's adversarial. In some cases, and it's actually going to be in the first part, it will be that they all start at the same location, and this same location is chosen by an adversary. So the first, yeah. But you can also study random initialization, definitely. Yeah.
Because in this case, I was thinking, I haven't worked in this area, but just I was saying that if we're making a transformation in the network, like a minimum spanning tree, that you have the smallest subset of nodes that actually you can connect to all nodes with the network, then maybe you have some boost in the initialization. It's just an idea. I don't know if it works or not.
Yeah, so the initialization is definitely a topic, and I've seen actually some papers on this where it makes, when it makes a big difference how do you initialize the agents. Yeah, but we just assume that it's the worst case, and so that we have a guarantee, no matter where they start, we are guaranteed that they will explore in this time. And so the properties that we are looking for is that the solutions are local and universal, meaning that we want, when designing more, so to speak, the model, we want the agents to be local, meaning that they communicate only with agents that are at the same location. They are not aware of any of the global parameters of the graph. We don't want any specific initialization of the system. And yes, and we want this to work for arbitrary graphs. And yes, and we start with this collaborative exploration using memory. Yeah, so agents have memory. And the model is as follows. So we assume that the nodes are labeled, so the agents can distinguish the nodes. Yeah, so the agent, when it visits the node, it learns the identifier, and also it learns about its neighbors, something about its neighbors. Yeah, so in this slide, I said that it learns the identifiers of its neighbors, but it's actually enough to learn the number of its neighbors. And initially, the graph is unknown, which is obviously, and this actually causes some problems, because when you start exploring, you don't know where is in which direction there are more nodes. Yeah, so you don't know if you have any freedom of choosing in which direction to send more agents. You don't know, because you don't know in which direction there are more nodes of the graph. Yeah, so that's why it's not so obvious. And the notation that we will use is that is d is the distance from the source. So r is the source, is the node in which all the agents start, and d is the distance from the source node to the furthest node of the graph. So this is the maximum length of the maximum path, let's say, in the graph. Yeah, so it's the distance to the furthest node of the graph. Yes? N is the number of nodes, and k is the number of agents. And there is one simple observation, is that any graph exploration algorithm needs time that is proportional to d plus n over k. I don't know if you're familiar with the notation omega. It basically says at least. And since we are lazy, we just don't care about the constant. So it's at least a constant times d plus n over k. And this is because at least one agent has to go from the source node to this furthest node of the graph, and this takes times d. You cannot jump any quicker. You cannot teleport to that node. So you need to, somebody has to travel to that furthest node, and every traversal of every edge takes one step. So you need time d. Secondly, you need to explore every of the n nodes of the graph, but you have only k agents, and every agent explores exactly, or at most, one node in every step. So you need time n over k. So this is a simple, say a lower bound. So you cannot beat this time. You cannot be faster than this. And actually, it happens that if you somehow magically know the graph, which is I told you that you don't know, but if you knew, then you actually could achieve exploration in time d plus n over k. And the way it's done, actually, so in our area we call this an offline solution. So an offline solution is a solution where you somehow know the topology of the graph. So if you knew the map of the graph, then you could plan the moves of the agents so that they visit all the vertices in time d plus n over k. And the way it's done is actually pretty simple. I should be able to explain it. So assume that we have a graph like this. It has n equals to 9 vertices. And our offline solution looks like this. We first fix a BFS spanning tree. So a BFS spanning tree is again some fancy term that basically says it's a tree, which is a graph without cycles, that spans, meaning that it connects all the vertices of the graph, and it's BFS because it has a minimum depth, let's say. Yeah, so the length of the longest path from R to any other vertex is not longer than it is in the graph. So
this is like a subset of the minimum of the set of minimum spanning trees, yes?
So the BFS it's an example. It's some particular spanning tree.
Yeah. So this
that has.
Okay, yeah, okay, I got it.
The spanning tree that has this additional feature that it does not, let's say, make the paths too long. Yeah.
Okay.
And what we do is we take these edges from this tree and we change them into two directed edges in both directions. And we get a funny graph like this. And you can see that this graph, you can traverse. You can do Eulerian traversal. It's another fancy term, meaning that you can just traverse all the vertices of the graph of this tree. For example, if you start from R, you can go to R, then to E, then to G, then back to E, then to F, then to H, then back to F, and so on. And with this, you can visit all the vertices of this tree, and you only traverse every edge once in every direction. Yeah, so you just do traversals in both directions of every edge. And so this circuit, this path, this traversal has length proportion more or less 2 times n. Okay, fine. So we take this cycle. So we just spread it around and look at it. And since we know the graph, so we know we can agree, the agents know the graph. They can agree to this cycle. And they can find positions inside the cycle that are equidistant and just place themselves there, just walk there. Yeah, so if we have 4 agents, they can look at the cycle and place themselves. I mean, decide one of them goes to node F, the second goes to node R, the third goes to node B, and the fourth goes to node D. And this takes D steps because D is the length of the longest path in this graph. So in D steps, it's enough to reach these nodes. So each of them simultaneously goes to these 4 vertices. And then they simply continue along the path, along the cycle like this. And each of them explores more or less 2n/k vertices. And this gives us the total time of D plus n/k. So this is a simple algorithm, and more or less this is a flavor of approaches that we deal with when solving a problems of exploration in such models. But we want to do something more interesting, namely what happens if you don't know the graph. Then you obviously cannot plan where to go beforehand because you just don't know where is most of the graph. So if you have completely no communication, there is no way to interact with anything, then there is basically nothing you can do. In some graphs, you cannot have any parallelization. So there is no benefit from having multiple agents. And so obviously you can study various models of communication. So in the global communication, the agents have like shared knowledge. Everything they have explored is immediately shared with others. You can have whiteboards where you just leave information at the nodes. And finally, the most interesting is the local communication where the agents leave informations when the agents exchange information when they are only at the same location. And so there are some crazy complexities that are obtained for as a state of the art for the trees. And so you might notice that it's offline, which is the time of the offline solution, times something. So if you want to explore online, which means explore unknown trees, so in this case, it's only tree exploration, not even general graphs, then you have to pay the offline times some additional penalty. Okay, and there is some upper bound that is definitely very interesting, but we'll focus maybe slightly more on the lower bound. So here it says, it's actually done by some people from Wrocław, that you have to pay, that the cost of exploration is always offline times some factor that depends on k. So you cannot get exactly exploration time offline. You have to pay some additional penalty. And we will actually want to do it faster than this, but using more agents. So the question is, can we do it in time proportional to d, to the diameter, using many agents? So assume that we have an abundance of agents, and you want to do it very fast. And obviously you can do it. You can do a so-called flooding. If we have, so in this case, let's say that delta, like the big delta, is the maximum degree of the graph. Then if we had delta to the power of d agents, which is ridiculously many, exponentially many, then you could do a naive flooding, which is just basically divide the agents at every node evenly among its neighbors. And so this would look like this. Yes, I have delta to 4 in the root, in the starting node of this exploration. After one step, I have at least delta to the power of 3 at every node at distance 1, at least delta 2 after 2 steps, delta to power 2 in every node at distance 2, and so on. And since the furthest node is at distance d, then I can do it in time d exactly, but I need delta to the power of d agents. So this is nice, but it uses a little bit too many agents. So there is naive approach number 2 that I will not maybe go into the details. You can actually do it in d square using only n agents. And so what we want is exploration in time proportional to the diameter, which is the fastest possible, like in this approach 1, but we want to use only polynomially many agents. Polynomially many is like, we don't want exponentially many. We want only n to the power of a constant, let's say. And these are our results. So we have an algorithm that works using many agents, because we need d, which is the diameter, times n to the power of c for some constant c that's greater than 1. And it works in time d times a constant that depends on c. So it's very close to the optimal. It's very close to d, and we actually even show a lower bound that you cannot get exactly to d. You have to use at least d times another constant that also depends on c. And we show this in the model with global communication, where this knowledge is somehow shared. But also we show that it's possible to translate it into the model with local communication, where the agents can exchange information only when they are at the same location. Yes, and initially our solution requires that the agents know the value of n, but then we again showed how to make it work without this knowledge. And how to do it is as follows. We assume that the agents appear in this route in some waves, let's say, of certain size x. And then we do, whenever we have a choice to split the agents, we split them proportionally to the number of leaves of the subtree. So first of all, assume that we are exploring trees. So this is like a simple simple case in this example, and assume that they have global knowledge, so they know everything that has been explored so far. So then they can somehow, they know the progress of exploration, and they split themselves proportionally to the number of leaves, which is somehow which translates somehow to the size of the tree that we know so far. And so this looks like this, more or less. So assume that we have these waves have size 9. So so there are 9 agents that are somehow appearing in the root in every step. And initially it looks like this. We have no knowledge about which subtree is bigger. So we first send we divide the wave proportionally, we divide the wave equally to every neighbor. And after step 1, we discover that actually one of the subtrees is much larger. So in the second wave, we send more. And after 2 more steps, we complete the exploration. So this is basically a very simple idea how to explore a tree. But actually, we struggled for more than a year to complete the analysis that it actually produces the desired complexity. Yes, so this is the time complexity of it.
Sorry, how, I didn't get it. How they learn that like, for example, in this slide, we have 9 in one wave, then we split them. So could you go back one slide? Yeah, so now I divide it equally because I don't know.
Yeah.
And now I see that this third from upper, counting from up, has a larger degree. So I need more agents there. But how I learned about this?
Yes. So in this example, you can think that they know immediately. Mm-hmm. And in this refined algorithm that we have for the local communication, mm-hmm. we send the messengers. Let's say.
Okay, because you told us that they can communicate only within one node, so that's why I thought, how possible?
Yeah, and it's I don't know if I have the slide with it. So here if the communication is global, you have this factor 1 over c minus 1. Mm-hmm. And if it's only local, so meaning that they can talk only when they are at the same location, it's 2 over c minus 1. So that's the only difference. And this difference is exactly to send this information back to the root, so they know how to how to split themselves. Yes, and we also have a lower bound that's not very hard to come up, because you just fool these groups of agents because they don't know how the tree will or how the graph will grow. So you just give them the larger part of the graph for the group that's the smallest, basically, more or less. That's how and I think I have like 5 more minutes. Yes. So.
Yes, exactly. Yeah.
So I would like to maybe advertise one model of graph exploration that's called the rotor-router. That's maybe doesn't deserve a fancy name because it's basically a round robin. So imagine that here we have a graph of 9 vertices, and there are 2 agents. One of them is blue and the second one is red. And then this is the model where the agents interact with the environment. So the environment has like pointers, and when the agent is at the node, it follows the pointer, and then the pointer is moved to the next neighbor. So in this example, the agents follow the pointers, and then the pointers get switched to the next. And here, if we have 2 agents at the same node, they do the same thing, but this pointer has a ability, let's say, to send one in one direction and one in the other direction. So they move like this, and they continue. And this is also a valid method of graph exploration, but here you can see that the agents have completely no choice. They just don't, they are just pebbles that are tossed around by these cannons of the environment. And this is a very, I would say, fascinating process to analyze. I also spent several years doing this. And one thing that's an inspiration is the random walk, because in the random walk, every node is basically sending on average the same number of agents in every direction. Yeah, so on average. In this case, it's deterministically. The agent, every node has this rotating cannon, and it's sending the same number of agents in every direction deterministically. So this rotor-router can be seen as a de-randomization of the random walk. And when it goes to graph exploration, so the time until every node has been visited by at least one of these agents, it's surprisingly close to time of multiple random walks. This is something that we found pretty interesting. So one thing that's maybe that's also funny is the way it looks on the path. So even the analyzing this rotor-router on a path is challenging. So here we have one red agent and one blue agent, and the gray nodes are, let's say, they have not been visited before. So this exploration looks like this. They somehow have some sort of domains. There's a blue domain and a red domain, and they are circulating around their domains. And they are extending them by stealing these nodes from the neighboring domains. And this process has a very funny behavior, because if the agent has a smaller domain, then it visits the borders more frequently. So it somehow has the ability to steal from the neighbors, because if the neighbor has a larger one, then it visits the borders less frequently. And it has a very funny behavior, but we managed to show that it has a slightly small speed up on paths. So if we want to explore paths using multiple rotor-routers, you have this log k. I don't know if it's seen here, a speed up. So it's slightly faster than using a single agent, because with a single agent rotor-router, the time is n square. If you have k of them, it's n square over log k. And it's a very small speed up, but still it is something. So we analyzed the time of exploration by analyzing this evolution of these domains, and we got this result. And it's actually the same for the random walks. If you have k random walks, they all start at one endpoint. The time until they get to the other endpoint is also n square over log k. And this was actually the first result like this. And it turned out that that the speed up is the same for many other graph classes. So on the left column is the random walk, and the right column is the rotor-router. And for most of the cases that we managed to get in the result, it was the same. And we got some results that are only a conjecture for random walks, and we managed to prove them for the rotor-router. And yes, and that's it, I guess. Yeah, so we showed the first algorithm is how to explore any graph in time proportional to the diameter using a polynomial size team of agents with local communication. And the second thing was this process rotor-router that can be seen as the randomization of multiple random walks. Okay, that's it.
Oh,
Thank you.
okay, thank you very much. And now it's time for questions. Although we asked many questions already during the lecture, maybe I will stop recording right now because maybe you will feel more free to ask questions. So I will stop recording.